Welcome back. This is Engineering 255, Engineering Statics. In this episode, we're going to look at the chapter 3. We are going to have two videos, and the first part of the video will cover section 3.1 to 3.3. The topic is about equilibrium of a particle. Now, when we talk about a particle, we don't need to worry about other situation which we will cover in the later part of this book. And that is if the object is a plane, is a body, then when you apply force at different point, this object might rotate as well. Over here, we just concentrate about the force without rotation. And what is equilibrium? Equilibrium is the situation when you have a net force equal to 0. And that is the condition we're going to use in this chapter to solve the problem. So section 3.1, we will say, tell you about the condition for the equilibrium for a particle. 3.2, we will look at something that you learned before, which is very important. That is the free body diagram. I would say free body diagram is the most important part of this chapter and could be the most important part for the whole book. Because if you can't have a good free body diagram, you might not be able to get a correct equation in order to solve the problem. And 3.3, we're going to focus on two-dimensional force system. So that is the topic for this chapter. So in this video, we're going to focus on what we just said, free body diagram. Okay, so what is the free body diagram and how can you draw a free body diagram in a correct way? The second thing is that you're going to use so-called equation of equilibrium. And that is the net force equal to 0 to solve a two-dimensional problem. So these two are the most important part of our topic for today. We always like to let you know how these can be applied to the real situation. So in here, we just give you one example. Look at the crane at here. This long crane is lifting a load, which is the bottom right here. And if you design this crane, you must know how much load can be supported by this crane. In order to do that, you need to do a force analysis. And that is the purpose of the statics. You wanted to know if that will fail or not, such that you can design the strength of the material. That could be the size of the material or the choice of the material. And how could you find those forces? To solve this problem, we normally start with a free body diagram. So on the right hand side, you can see this one here is a simple version of the free body diagram of a point, where the point is actually this point right here, the straps. Underneath the straps, you have a load, which is like a cart, possibly has something inside of this cart. Above the strap is a cable that provides with a tension force right here. And the cart itself has a weight. So the weight is the load that will apply to this strap's intersection point. And we can do this simple analysis to understand how much tension is going to apply to this cable, which certainly is going to be equal to the total amount of the load that is supported. Let's look at another example. Here you have a spool with a given weight, which is right here. And how can you find the force on the cable There's several cable here. You have a cable A sub B right here to here, and you also have a cable A to C. So these two cables are going to support the spool. The spool will give you a load, and you also have a pulley on the top, and the pulley is going to connect it to the crane at the point of D. Now, when you do a free body diagram, you have to choose a point that you want to isolate. If we just wanted to focus on this A, which is a ring at here, and you can make a free body diagram just around this point here. And we need to identify how many forces are connected to the point A. In this case, you have a tension, which will be the cable from A to D. You also have two cables that connect to the spool, which is the tension of B and tension of C. And we can use this way to do the analysis. Now take a look at the third application. Then we have a boat with two cables and connected to the point of B, which is a towing pendant. And it will connect to another cable A that will be tied to the bank. What are the forces in this brittle cables? What size of the cable should you use? To make that decision, you certainly need to determine how much of the force are going to be held by each one of the cable. Should the cable A to B to be the same size as the cable from B to C and also from B to D? If BC and BD are shared in the load, I would say the cable of A and B will support more of the force, which is 50,000 Newton, than those two branch of the cable, right? And if you are given with an angle, where the angle are different, then how do you do the calculation? So this is the problem that we're going to solve in this chapter. Now I hope that you understand how to make a free body diagram right now. Always when you do a free body diagram, you have to select the point that you wanted to isolate, and then you are going to identify the forces that connect to that point, and you do the analysis based on the configuration of the force applied to that point. We're going to use this example here to explain what if you want to solve a situation and that situation is a coplanar force system. Coplanar force system simply represent this is two-dimensional. So we only consider about X and Y. Over here you see a picture that we have a weight at the bottom, which is the C. This weight is 40 kilogram. This is not the weight, this is the mass of this weight. In order to find the force, we have to multiply with the G, right? So 40 times G is going to be the weight at this point. And this will have a cable connect to the point A here. With A, you have three cables. One cable going down, two cable, one go to the left, and the other one goes to the B, which is the up right corner. We want to determine the tensions in the cables, and how do we do the free body diagram, and how can we apply the equation of the equilibrium to solve it. So what is the equation of equilibrium? This is based on what we talk about in the chapter 2. You have to find the summation F equal to 0. And because we are looking at a two-dimensional, we can separate this f into two different components. That will be the f of x I plus summation of f of y of j, that will be equal to 0. This vector equal to 0, meaning f of x has to be equal to 0, f of y has to be equal to 0. So our condition for two dimension, you can think about, you simply need to find what situation can you get f of x equal to 0, what is the condition that you're going to get summation of f of y equal to 0. And this is what we call equilibrium equations. Okay. Let me emphasize how important this free body diagram is. Okay. I wanted to repeat this because this is really the most important things that you need to know. And how do you draw that? That is the basic things in order to get a good equation to solve. So under here, we look at the what and why. The what is that doing the free body diagram is to show all the external forces acting on the particle. So how many of the force applied to the same point is what we try to draw. And why is certainly just because if you identify those forces, then we can write the equation of the equilibrium. So if you focus on this point here, you can find several different forces acting on this point, and if that is the case, then you can use summation f of x and summation f of y to solve the problem, right? So when you draw this, make sure that you draw the angle if the force is not along the x or the y direction. So if you have this is the x and y coordinate, and this force is just along the x, this force just along the y, so I don't need to worry too much. However, for this force, you are not on the x or y axis, then you have to mark the angle. So we're going to mark this angle, and with the angle we can decompose the force into x and y component. Let's use this one, which is the one that we showed you before, to continue to show you how we draw this. When you do a free body diagram, first that you have to identify which point that you want to isolate. So you are isolating which part of the system. So isolate, when you isolate, that means you cut off anything connect to this point. So we cut this one free from its surroundings. So in this case, when we focus on the point A, we're going to cut off this cable and this cable and this cable. Let me just use different colors so you can see where we cut. We cut this one, we cut this one, we cut this one. And whenever you cut off something, the Newton's third law tells us when you cut off something that you're going to have a reaction force. So when you cut something connect to the object, you always going to have a force. For a cable, you cut off a cable, it will always give you a tension force. The cable can only support a tension force. So cable cannot support compression, because if you compress a cable is going to slack. It's not going to give you any of the force. So cable only used for a tension. And tension always get away from the object. So if your object is this one here, our tension force is always away from the object. So it will go outwards away from this point. So this is going to be your tension force. Same thing for this one. You cut this one out, you're going to have a tension force here. This is going to be a tension force away from the point A. You're going to have three forces, and that is what we draw at here. You have point of A is the point that you are interested. You cut off these three cables, and they are tension force, and you mark each one of the force with a different subscript. Sometimes people like to write F of AB, which represent the force along A and B, or you just simply write this is the force of B, which is the point it connected to. Notice that we put an angle, right? So because this force is not a force along X or Y direction, we wanted to write the angle between the X-axis and your force direction. This is the free body diagram of A. Now, if you know some of the information, you certainly can write down how much of the force that is attributed to that point. In this case, we have 40 kilogram right here. Does the 40 kilogram represent the tension force of A? How do you know this is the tension force of the cable AC? Well, if you do another free body diagram, you will understand why is that. If I do another free body diagram right at this point, so this is the point just right above the weight. By assuming this is just a single particle, all the weight is going to apply to this single particle. And the weight is toward to the center of the earth, so it's going down. This is the weight, which is equal to m times g. When I look at this point, I'm going to cut off the top. Remember, when you cut off something, you always to draw a force, which is a reaction force. This force is a cable, so it's going to be a tension force. Tension force will away from the object. So this is the tension force. That is the tension force of A and C. This force and this force has to be the same because they are equilibrium. So by looking at this point, which is the point just above the weight, I know this AC force, which is the F of C, is going to be the same as the weight. Therefore, you can write F of C equal to 392.4, which is 40 times 9.1, 9.81. Sorry. Okay. After understanding those, you make a perfect free body diagram. Now we are ready to solve the problem. After you finish the free body diagram, identify all the unknowns in the diagram, and with the information that you can draw from the statement of the question, then you can write the equation of the equilibrium. Our condition is this point A is going to be a static point because the point A is not going to move. In a case you hand away at the bottom, two cable go to different direction, will hold the point A to be static. So we can use the particle in equilibrium. And we just told you when that is the situation, you have a net force equal to 0. This net force is coming from the 3 different components, the F of B, F of C, and F of D. We have only like 2 directions, which is X and Y. So we can represent each one of the force in the X and Y component. Let's start with the C. The F of C is only at the Y direction, and as a matter of fact, this one is negative Y direction. So we can write F of C, if you want to write F of C in a vector, this will be 0 of I, and it will be negative 392.4 of J. This is a negative because it's going down, and this is only in the Y direction, so we have J at here. If we look at F of D, which is a vector here, F of D is a vector, we don't have anything on the Y direction, but we have X direction. It is in the negative X direction, so we can say this is a negative F of D if the F of D represents the magnitude of the force. That will be I plus 0 of J, because there's no Y component here. Last thing we wanted to look at is this one here. So F of B. The F of B is not on the X, it's not on the Y. It has an angle, but we can decompose this into 2 different components. So in the X direction, let's write this. X direction, we have F of B, which represents the magnitude of this force, multiplied with the cosine 30 degree. This represents the X direction component, and we also have Y component direction, which is going to be sine 30 degree. Both are positive because they are on the first quadrant, going to the right, going to the top, so they are all positive. And then what you need to do is simply just write this in a scalar form to make summation f of x and summation f of y equal to 0. Then you solve the problem. So how many equations are we going to have? You're going to have 2 equations. And how many unknown? We have 2 unknown, that is fd and fb. fc we already know is negative 392.4, so you don't need to solve this f of c. And that's how we solve this problem. So here we just give you all the number, and if you look at the previous slide that we show you, we have this equation represent x direction, and I like to use this kind of a way to represent how we sum things together. If I draw an arrow represent the direction, and we put positive sign here saying that in that direction is the positive direction. And you have summation f of y, which are these 2 components. This is actually coming from the f of c, and this is the f of b in the sine 30 degree, which is the y direction. You solve these 2 equations, you got the answer of these 2. And remember this one here and this one here, they are vectors. So when we ask you the answer, you should also put the direction in addition to the magnitude. Okay, this is very important. I will take off points if you miss the direction. So you have to make sure that you put a direction. Okay, Let's consider about some other possible forces before we move on to the rest of the book. One of the very common forces that you will see in the book is what we call the spring force. The spring force is determined by two things. One is how strong the spring is, which we categorize that by what we call the spring constant, and we use K to represent the spring constant. So spring constant will represent how hard or how soft the spring is. If you can easily to extend the spring, that means this spring constant is going to be small. If it's harder, then the number will be larger. The second thing will determine how much of the spring force is how much of the deformation of the spring. That means how much do you extend that. So this change of the distance compared to the length that without any of the force. This L of 0 normally we will say is the length of the equilibrium. That means the spring doesn't under any of the load. That's the original length. When you apply a force, it's going to change its length, but at the same time, it's going to create a spring force. So the spring force is going to be proportional to how hard the spring is, which is spring constant, and how much of the deformation, and that is the spring force. Spring force is always opposite to the direction of the force that you apply to the spring. So if you pulling down, you make it stand, the spring force actually going up. Okay. The second common kind of a force that we want to talk about is the cable and the pulleys. We told you before already, when you are looking at a spring, when you look at a cable, it only provides a tension force. Okay, cable can only provide the tension force. Let me make this one big marker here. Okay, the tension force always pulling, which means the force always away from the point that you are looking at. It's always, and the second thing is that it's always in the direction of the cable. Okay, so if the cable is going vertical, that force should be vertical. It will not be a horizontal. If the cable is not horizontal or vertical, it has certain kind of direction, like this one here, this cable, then the force will be along this direction. And pulley is the element actually provide a way to change the direction of the force. So the function of the pulley simply is to give you a way to change where the direction of the force is going to be. So sometimes you can change the vertical force pulling on the horizontal object. Sometimes you can have like two different direction, like this one here. You pulling from this vertical one, but it's going to change how object going along this direction. So pulley, normally we assume the pulley is not going to have friction, but in realistic, pulley will have a friction, and we will consider friction in one of the chapter in the future. If they give you assumption pulley is not going to give you any of the friction, then you can ideally think about the pulley simply just an object to change the direction of the force. The next one we wanted to show you is what happens if you have a smooth contact. A smooth contact meaning there's no friction as well. And if you have an object is resting on a smooth surface, the surface will exert a force on the object, and that force has to be normal to the surface. This is what normally sometimes people say a normal force or contact force. Okay, so you can say this is more like, put this one back. This is a normal force. Oh, this is just a contact force. So here you have a circular disc, and here a contact to this ramp. The ramp has 30°, and as a cable is pulling at this direction. They give you a direction with an angle of 20°. If you make it an XY coordinate like this, then this angle is 70°, right? Because it's a 90° from X to Y. So this is a Y, this is an X. When you wanted to analyze this object right here, you're going to isolate this object. When you isolate this object, you have to eliminate this ramp. However, the ramp actually has a force, so you have to write a reaction force to this pulley or this disc here. And what is that force? The force is going to be the force that coming from the ramp to the object. So this force is this force right here, the smooth contact force, which is the normal force that we use N to represent it. And this is happening because you remove the ramp, which you give the support to this object, and this always perpendicular to the surface of the contact. So this is always going to be perpendicular to this horizontal direction right here. Okay, and that is the normal force. Now it's important that you understand how this angle is. How do you know this is a 30° right here? Let's make a picture to show you why this one is 30°. We have a force perpendicular to this direction, right? So this is a perpendicular. I didn't draw right and below here because I don't have enough room, but you know this one is 90°. So let me redraw this one right here and make it a little bit larger. This is our end force right here. This is 30°. And this is a 90. So what is the angle? This should be 60°. I'm going to draw another line to help me identify what is the angle that this force respect to this vertical direction. Right. This is what this angle is. Why do we know this is 30? Because this is also perpendicular to this bottom part. And this is 60, then this one has to be 30°. So this is 30° right here. All right, let's use another example to help you understand the concept of this chapter. And we're going to review what we just said. The first thing you do is to look at the problem, understand what the problem is telling you, collect all the information that you have, and that including what are the forces acting on the point, what are their angle, can I find some of the information about some of the forces. If I do, that's great. Then you solve less of the equation to get the answer. So what is given for this question? You're given a box, the weight is 550 pounds, okay? And the geometry is shown as the graph. So this is the weight. This is the unit not in the Newton, but in the US custom unit system. 550 pound itself is a force. So you simply just use 550 pound. This is the weight. The force in the rope of AB and AC are the forces that we try to find out. And AB is going to be the force that go along this one here, because this is a cable. The cable force always go along the cable and is outwards. AC is going to be force at here, and also this is a tension force, so outward of this point of the connect A. What about the force going down? This is another cable, and we know this force is going to be equal to the weight, because we just showed you in the previous example. This force is the weight of this box at the bottom. So you do the free body diagram, you simply draw. This is the point, a particle that we are interested in. We have three different forces connect to this point. This is our FAC, this is our FAB, and this is our F of AD, which is equal to 550 pound. All these are not, should be a vector. So if I draw this one as a vector, this one is a vector, and I put this one as a vector, then I have to put this one as negative 550 mj. So then let's just clean up to redraw this picture. This is the point of the interest. We have 550 here, two force vector here. This one we use 3, 4, 5 triangle to represent the direction. This one we have 30 degree with respect to the negative x direction. And we can start to decompose each one of the force into the x and y component. For f of x, in this direction to be positive, what are the forces that are acting on the x, y axis? This one is not going to make any of the difference on the x direction because it is purely just y direction. We have component from this one here. You can decompose this force into the x direction at here. This will be the FC at x. You can decompose this one here. This will be f of b of x. So you sum these two together, and then you can get this equation right here. Now this one is negative because it's on the opposite side of the positive x direction. This one is 4 over 5. Why is it 4 over 5? This because this is a 4 here, and this is the hypotenuse, and we're going to use whatever the length at the x direction divided by the hypotenuse, and to get the component of x direction. Similarly, you do the y direction. When you do the y direction, this one will make contribution to the y direction, which is negative. That's why this one is negative a here. And you have two equations. Your unknown is FB and FC. You solve these two, and you will find out this F of B is 478 pounds. FC is 518 pounds. Now, you should also make the drawing of the direction. So this part here is the direction. If I want to mark this direction, I will use this way to draw the direction. This will be the direction of my force, and I will put 30 degree at here. If I wanted to represent direction of the F of C, I will use this way to represent it, and you use like a 3, 4, 5 at here. This is how you represent a vector. So you can use either put the angle or use the triangle, the small triangle, to represent this direction. Here's another example. We just wanted to show you more examples so you understand how to do this kind of problem. So this is a different from the previous one because it add another weight at the C here. And it doesn't give you the weight of A. And we still have 3 cable connect to the E. However, there's another cable that is connect to the pulley at the point of B. And pulley, again, is the device that can change the direction of the force, right? So if you look at one side, which is this side, direction is along this cable. On the other side, this is the direction of the force on this pulley here. We want to find the tension in these 3 different cables. That means you have 3 unknowns. Didn't we just have 2 equations? How can we solve 3 unknowns with 2 equations? Well, in order to do that, you probably need to do not only just one free body diagram, you probably have to do 2 different free body diagrams. So let's see how we do this. If we only look at the point of the E, which is this like a ring at here, you cut off the bottom, you have a tension force going down. You cut off this one here, you have tension go to the left, right? You go this one, you have tension force going down. You cut off this one here, you have a tension force going this way here. And what is this tension force equal to? Well, this force is going to be the same force that is on this cable. Because a rope will have the same amount of the tension, doesn't matter where the rope that you cut it. So it's always going to carry the same amount of the tension. You don't make this point as a free body diagram point and you try to say, oh, this is a force at here, there's another force at here, and I'm going to do, like another free body diagram, try to figure out this force here. We would deal with this in the later part, but not at here. You could still solving that kind of situation, but when you do that, you're going to have some other force shows up. But in this case, just make it very, very straightforward. For a cable, it has the same tension force at any point of the cable. Okay, it will not change even though the direction is different. So this force at here, this TEB, is going to be equal to the weight of this one here. Okay, and if you understand this one, then the problem becomes the same as the previous one. You just had this one, which is given. You have to decompose this one into x and y direction, and this one is simply just y direction. This one is x direction. This is a negative, this is also negative, and you solve these 2 forces, and there will be 340 to the left and 196 going down, and that is how you solve this problem. Okay, so I hope that you understand how we solve this kind of problem. The most important thing, again, is that understanding how you make the free body diagram. This is the end of our first part of the chapter 3.